sometimes the number of the independent variables that we have is more than one. So the dependent variables depends on more than one independent variables. For example, in this figure you see a plane that we have two x1 and x2 which are independent variables, and we have y which is a dependent variables. And this plane that represented by a black gray area is a two-dimensional regression model, two-dimensional linear regression model that has x1 and x2 as a parameter. In general, we can have a linear regression function that has k dimension. So the regression function that we have is b0 plus b1 x1i plus b2 x2i and so on. So we can have multiple regression coefficient here. In this way, the similar way that we had for one linear function with one parameter, we can use minimizing error squared, sum squared, to find each of the parameters, each of the value of the bi's. But still we can use a built-in regression analysis tab of the Excel file that we have. So that means we can use still regression tab of the Excel file that we have. The question is now how we select the parameters, how we, for example, in this example we have a price of the house that is function of the square feet of the house plus the size of the garage and the number of the bedrooms that we have. The square feet is in 1000 square feet, and then we have guessed that the price of the home is function of these items. Now the question is that do we need to use all of the three functions, all of the three independent variables, or we have better function that uses only one or two of these parameters? If we use blindly all of the three functions, all of the three independent variables, we may end up having overfit. That means the function is the function, the regression function that we are getting may perfectly find these values, but whenever we have any values outside of this range or outside of these values that we have here, we may get a different answer which is not providing a good solution for that. In other words, we may poorly predict the values that we have outside of this range. So in this case, it's better start out by each of the variables and find out the regression function for each of the variables and compares the errors or r squared and select the one that has a higher r squared. Remember, r squared is the one that says how much is how many percent of the function is catching the good result. So r squared is we can consider as a best estimation that which function is a better representation of this model. So here we have to first do three regression analysis that we can conduct. So we can use data and data analysis, and in the regression type, so we can select yi's here, and then we can select square feet as a input parameter, and we represent this one as a x1. So this is gonna create one new tab, new worksheet, and you can see that we have the result in this section, and r squared here is 8.86. But we have one more better item, one more better factor, which is adjusted R-square. This adjusted R-square is modification of the R-square that consider the number of the observation and the dependent variables. So R-squared is a better one. Also, we can use a standard error. Also, that's also better one. You can see in terms of the adjusted R-square, we have to, the model is better if it has a higher adjusted R-square. And if we want to judge based on the standard error, the model with a smaller standard error is the better one. So this is X1. Now let's run the model, another regression model using another independent variables that this time is a number of the garage, and we represent this one by X2. So let's represent this one by X2. And so let's represent this one by X2. Now this is the result that we got for X2, and you can see that both adjusted R-square of this model and standard, in terms of both of these factors, the X2 is worse than X1. Compare these two values. I'm gonna copy this to next sheet that you can see them. So you can see that X1 has a better adjusted R-square, and also it has a better standard error. Now run the model for the third decision variables and see how does it affect the model. So we select the Y variables, and also we select the third decision variables. And now we represent this model as in another worksheet, X3. Now we got this one. Now, so these are the adjusted R-square and the standard error, and let's compare this value by the other decision variables that we had. This one is for X1, this one for X3, and we are in the, and these are the value for X3. So you can see that X1 has a better adjusted R-square comparing to X3 and X2. So X1 is the one that we definitely can choose. Also, let's compare about in terms of the standard error, and you can see that X1 also is better in terms of the standard error. So it means that X1 is a good starting point as a in the regression model. We should have the X1. Now let's add one more parameter, one of these independent variables to the model. So we can add either X2 to X1 or either X3 to X1. So we assume X1 is the one that we have in the model. Now let's add the either of these two. Let's have first X2. So here we are running that we are using X1 and X2. So this is gonna be, so this is X1, X2. Now this is the result that we got. So again we have this is the first time that we are running the regression model using two independent variables. As you can see, the regression degree of the regression is 2, and the number of the observation we had 11. So the degree of the freedom of total becomes 11 minus 1, so which becomes 10. But the residual, remember that the residual is total number of observation is n, and the number of the independent variables that we have is 2 and -1. So this is the degree of the residual that we have. So anyways, we get the adjusted R square and standard error for this model compared to value of the x1, which was 0.89 for the adjusted R square and 10 as a standard error. We improved this value by 0.9, 0.92 and 7.47 respectively. So you can see that we are, by adding x1, x2 to x1, we are improving the model. Now let's add x1 and x3 to see the result. Now we add, so let's work on the x1 and x3 so we can replace the position of the x1 and x3. So we just deleted x1 and x3, we just deleted x2. So let's bring the regression model here. So this is out y, and then we have x1 and x3. So this is the result that we get for x1 and x3. Now let's compare the result for in terms of the adjusted R squared and the standard error. Let's copy this value to x1 and x2 page and compare it. And you can see that x1 and x2 has a better R square because it's higher, and also it has a better standard error. So we can see that x1 and x2 is a better model if we want to have a regression model using 2 parameters. Now let's add x3 to the decision variables that we have. So now let's have a model that it has 3 independent variables, x1, x2 and x3, and see them. We run the model. We select the output, which is here, and then the inputs are here. Then we call this x1, x2 and x3, and comparing the result, this is the adjusted R square, and compared to the value of the x1 and x2, which we make the conclusion that it was better. Let's compare it. So you can see that in terms of the adjusted R square, surprisingly x1 and x2 is much better, is slightly better than x1, x2, x3. Also in terms of the error, you can see that in terms of the standard error, we see that x1 and x2 is better model. Now the question is why by adding in one more parameter we are getting we are not improving the model in terms of the standard error or in terms of the adjusted R score. Here we have a situation that we call collinearity. That means some of the variables are depending on each other, so they are representing somehow the similar information. For example, here square feet and the bedroom are almost, they are representing the size of the home. You know, the higher the number of the square feet, it can in a way be correlated to the number of the bedrooms. So if we have a higher number of the bedrooms, then we have a higher number of the square feet. So here we can ignore the bedrooms as the third parameters, and we can get the estimation of the price by using just 2 parameters. Now let's look at the decision variables. Now let's look at the value of the parameters of the regression models that we have. The regression models that we have, it says the intercept is 127.6 and the B1 is 38.5 and 12 B2 is 12.8. Now we can have compare the lower and upper value 95% of this parameter, and we can see that these values are, none of them are 0, so none of them are include the 0, so that's means that the chance of the being 0 for each of these parameters are slightly less. Also, you can make the same conclusion from the p-values. You can see that p-values are small values, so then the chance of the being 0 for these parameters are less. Now let's look at the indifference significance of f. Here the significance of the f represents the situation that is there any of the betas has a chance of the being 0. This says that's impossible, so the model that we are getting is a valid model. Also, we can have some residual plots and compare the assumption about the error, that whether they follow a normality or not. Let's have the look at those residual one more time. We didn't plot those values, so let's have the just x1 and x2 and see the residual and the residual plot as well as the normality plot and check them. Now this is the x1 and x2 that we got, and you can see that we have two residual plot for the decision variables that we have, and you can see all of them are centered in the 0. Their average is pretty similar and they're in the 0, so the normality the residuals are okay in terms of the assumption that they have the mean of the 0. Remember that we are using two variables, two independent variables, then x1 and x2, and you can see both of them are satisfying. Now in terms of the normality assumption of the residual, you can see this is pretty similar and is a straight line that is slightly increasing, so we can say that the normality also is satisfied. So the mean is 0 and the normality is satisfied, therefore our assumption and our model is a valid model. So these are the, let's have summary of the what we discussed. So when we have multiple parameters, we have to solve for each of the parameters. We have to get the model based on each of the parameters that we have, and then make the conclusion based on the adjusted R squared or standard error. Both is going to end up the same conclusion, and we can have the parameters too, but we just make conclusion based on the either R adjusted R2 or standard error, and then we pick up the one that has higher fitting, higher percentage. For example, R2 is R2 for x1 is the highest one, or SE, so we can choose x1 here. Also, if you want to make a conclusion based on the SE, we have to look for the one that has the smallest SE. You can see the x1 has the smallest SE or standard error, so we have, based on the both parameters, both decision criteria, we choose x1. Now we have x1. Now we have to choose x2 or x3, so we can have a model that has x1 and x2 or x1 and x3. So we can have a regression model that has two parameters, x1 and x2. So we have to investigate both of these functions, and if we run this, we are gonna get there is summary of the result this way. And you can see that by adding x2, we are increasing R2 and we are improving the SE, so the error is decreased. But when we add the X3, the error is increasing, R2, the SE is increasing, and adjusted R2 is decreasing. So that means adding X3 is not good. So X1 and X2 are the better model. Obviously, if you add X3, because here you saw the effect of X3, so we can make conclusion right here that X1 and X2 are perfect. But for the to be clear, let's work on the X3 too. So we have X1, X2, and then we have another model that has a 3 parameter. Now, if we do this analysis, you can see that for the X1 we had R2, and we improve it R2 by adding X2, and then now we add X3. You can see that here we are not improving, we are decreasing R2, adjusted R2. So X1 and X2 is probably better model for describing this data set that we have. Now let's have make a prediction using this model that we created. Let's say it has a 2.1 square feet and a 2-car garage. So for the X1 we put 2.1, and for the X2 we replace by 2. And if we do that, we are gonna get this value for the yi hat. So this is the estimation that we get for the price value of the house, that it has 2,100 square feet and the 2-car garage. Now we can have a estimation 95% of the prediction level for this estimation that we have. It's just we need to add and subtract 2 times of the standard value of the model that we have. The standard error that we got for the X1 and X2 is this value that you can see. So this is a value that we can add 2 times of this value and subtract 2 times of this value to get a prediction. This 2 is a number that we have to use from T distribution, but for the purpose of the practice purpose, you can just use twice of the standard error and add or subtract from the value that we got for this price estimation that we have. So that provides the lower prediction interval and the upper prediction interval for each of the value that we have. Now, so far we talked about the linear regression, but in some cases it's possible that we have a non-linear regression model. You can see in this graph the relation between the independent parameter and the dependent parameter is not linear, so the linear function is not a good fit for this case. Here we can use a non-linear function, that is our regression model is a polynomial function. It's a non-linear function which has one of the decision values, one of the independent variables are taking some non-linear degree, for example 2 power of 2. Still we are not sure about the power of 2, but we can use this. Now to do the regression in this case, we can replace x12 by another parameter, which this parameter is equal to x12. So basically we are converting this nonlinear regression to a linear regression by replacing one of the parameters by that we have. So basically we are treating x1 squared as another parameter and as another independent variable. So this becomes a linear regression, and we already talked about the linear regression, so we can deal with this situation that we have. Now let's have an example about the nonlinear regression. So this is a data set that we have. It has x1, and you can see here, and we have the price of the house that we have. So let's first plot this and see whether we should have linear regression function or nonlinear function. So let's select the data. This is the x, and we have y, that are the dependent variables. And you can see it's a pretty nonlinear function. So you can see that the function is pretty nonlinear, so we have to apply a nonlinear function. For this purpose, let's see it more clearly. You can see the function is pretty much nonlinear, so let's apply the nonlinear regression for this purpose. And now let's try the x squared. So I introduce a new variables, new x2, which is x1 to power of 2. So, and because we have to use in the, let's have this parameter here. So this becomes 1 to power of this value, and use for all of them. Now this is all of the variables that we have. Now let's do the regression analysis. The y that we have is here, and then we have output here. So this is the intercept and the B1 and B2 that we have. So our model becomes 294.9 plus x1 minus 203.3 times x1 plus 83.4 times x1 to power of 2. So this is a regression model that we get for this one. And then let's plot this function. So let's use this regression model that we have here, and so this is, and compared to the value that we have, so this becomes intercept, and then we have this times b1 times x1 plus b2 times this value, then compare the result to the original values that we have. Let's plot this value too on this graph that we have. So select the data, x, and you can see that we are pretty much getting the pattern for this one. So this is how we apply the nonlinear function, nonlinear regression model. Now it's possible that we have multiple nonlinear parameters, multiple nonlinear independent variables. We can similarly apply those situations. Here we can replace x13 by another decision variables that its value is x1 times cube of the x1. So this is a way that we can deal with the polynomial or nonlinear regression model. So this is the end of the chapter 9, and thank you.